Good afternoon, ladies and gentlemen. Welcome to our second talk for the afternoon ET1 track, Optimization Techniques with OpenVINO to Enhance Performance on Your Existing Hardware. Anyone in this audience who's tried to build an AI system knows, you start with typically a framework such as PyTorch or TensorFlow. You train, and then you want to actually run inference. And you want your inference to run as fast as possible, but you also want it to be as accurate as possible. And you'd like to be able to optimize for latency or throughput. You'd like to have it run correctly on a range of different hardware. You'd like, ideally, the system to auto-discover that. And that's what we're going to hear about today, how OpenVINO can do that for you. We're lucky to have our speakers, Ryan Loney, who's a technical product manager at Intel, and Nico Galoppo, who is a principal engineer. Ryan, thank you.
Thanks, Phil. Hi, so I'm Ryan Loney, product manager at Intel for OpenVINO, and joined by Nico. Ansley, who was supposed to present with me today, she actually has COVID, and so she wasn't able to come. And so Nico fortunately jumped in. So kick it off here with sort of a problem statement or a challenge. So imagine that you have trained a great neural network, like Phil said, TensorFlow, PyTorch, solving a problem, something like anomaly detection, object detection, and you're ready to deploy it into production. So you have a few choices. You could deploy it on a GPU. You could deploy it in the cloud. But what other option do you have? You can also look at deploying it on maybe just a CPU. The great thing about OpenVINO is that you can do all of the above, right? So when we think about a CPU, it's more than just a CPU. So we'll talk a little bit more. Nico's going to talk about some of the techniques of how to optimize. But when you think about this Intel CPUs, we have integrated graphics, integrated GPU that you can use for running deep learning inference, and OpenVINO helps you unlock the potential of your CPU, your Intel Core processor. So use cases, you think of an X-ray machine or an ATM or maybe a robot that delivers packages. These are all devices that will have likely an Intel processor that you can use for inference. One of the common myths that we run into, I borrowed this slide from our developer evangelists. They hear this a lot, that running inference on a CPU is slow. And they're not wrong. So if you think about taking a model in PyTorch, trying to run inference, and then seeing the result, well, it's not always going to be optimized, so you need to do a little bit of work. And that's part of where OpenVINO comes in to make it easy. So OpenVINO is the solution, especially if you're trying to deploy on Intel CPUs, Intel accelerators. OpenVINO stands for Open Visual Inference and Neural Network Optimization, but we've recently expanded to natural language processing and audio use cases. So things like question answering, text-to-speech, speech-to-text, other use cases beyond vision that we've begun optimizing. It's called open because we're open source. We have an open ecosystem. And the OpenVINO tools and runtime are all open source software. The developer journey, so we talked about training the models, creating the models. That's the beginning. Build the model, use OpenVINO to optimize, and then deploy. So whether you want to deploy it using our C++ runtime, C, Java, Python, you want to serve the model. We have a model server for serving the model. You want to connect with something like GStreamer, we have all kinds of options for you to deploy. So this is a zoomed out look at the developer journey, looking at it another way, taking the models that you've trained, using the OpenVINO tools to optimize. We're going to talk about what that means in a minute. So things like operation fusion, convolutions fusion, doing filter pruning, quantization. We have a lot of different tools that can help you to get the best performance on CPU, GPU, VPU devices. And there's many ways to install OpenVINO. So if you scan this QR code, it's going to take you to a tool that'll give you all the different options for downloading the runtime and the developer tools from OpenVINO. We publish containers on Docker Hub, Azure Container Registry, Red Hat Container Registry. We have package managers for Linux, so if you want to quickly install the runtime on Ubuntu, on Red Hat. And if you want to use our developer tools, it's really simple. You just pip install OpenVINO dev, and you get the OpenVINO developer tools that Nico's going to talk about next.
Thanks, Ryan. All right, so as Ryan already said, with OpenVINO, we have a range of tools for optimizing your inference. And to start off, we have the model optimizer. So the model optimizer is an offline tool that lets you optimize your model independent of the target hardware. So you basically take your model that you've trained in TensorFlow or PyTorch or any open source framework, and it converts that model into a representation that OpenVINO understands. That is not just converting, it's actually also optimizing. So things like filter pruning, graph optimization, fusing certain operations, like for example, you could optimize by fusing a batch norm linear operation into a convolution operation into one convolution operation. So using this tool is actually really easy. All you need to do is provide your framework input model file, and then also provide the data type that you want to run your inference at, whether that's 32-bit floating point or 16-bit floating point. So here's, for example, the set of operations that would come out of a training network. And after it went through the model optimizer, you end up with something that's leaner and that obviously runs faster. And so then you've converted your model and into something that model optimizer understands. Then you probably want to know how fast it runs, right? And you probably want to do that without having to go through the entire process of integrating it into your application. So OpenVINO actually provides a tool called the benchmark app to do exactly that. So it can tell you how fast your model will run on a specific target device without kind of any of the overheads that an application would have. So really, your speed of light, if you wish. All you need to do, it's really easy to use. All you need to do is provide the model IR and then the target device. And that device could be anything. It could be a CPU, a GPU. It could be multiple devices at the same time. In fact, if you look at the data here that came out of the benchmark app, you can see that for this platform that has both a CPU and an integrated GPU on the top, the inference will, or the throughput will be much higher when you run with both devices simultaneously, as opposed to only running it on the GPU or only running it on the CPU. So the data on this slide is for 30-bit floating point. So what if you want to run your model faster, right? And how can you do that? Well, one way to do that is to compress your model. And compressing your model, the first way to do that is by running your model at a lower precision. Another way of saying that is by quantizing your model. So we go from a 32-bit representation to an 8-bit integer representation. And we have a tool to do that for you. The tool is called the Post-Training Optimization Tool, or POT. And this tool lets you do this without actually having to retrain your model. All you need to do is provide your full precision model and a representative data set, and then the tool will use that data set to kind of calibrate the quantization. It'll look at the activation, the ranges of values that come out of the model when you run that representative data set through the model, and then uses those kind of limits to calibrate the integer representation. So the tool is really easy to use. And typically in most vision cases, it really ends up in providing a model, an integer model that doesn't lose a lot of accuracy, typically below like a 1% drop of accuracy. Now, if you need more accuracy than that, then you might want to use another tool that we have, and that's called the Neural Network Compression Framework, or NNCF. This tool actually will perform retraining of the weights of your model at a target precision. So say you have a model that you've trained in TensorFlow or PyTorch, then the tool provides a few different algorithms or methods to come out with a compressed model. The first one is quantization-aware training, and this is where we're going to do at least a few epochs of backpropagation of your model and your weights at a specific target bit depth, whether that's 8 or 6 or 2 or 4. Mixed precision quantization takes that one step further, because if you really want to get a really good balance between accuracy and throughput, then you want to pick the number of bits that you're going to operate at for each operation in your model, so for each layer. And so that's why it's called mixed precision, because you're actually going to use different types of precision at the different layers of your model. And then finally, we also have filter pruning. That's where you kind of take away certain operations within your computational graph, and you're obviously going to take away those operations that don't really matter for the end result. And so the tool actually lets you do that and come out with a compressed model that's much smaller and has less operations, and therefore runs faster. And you can all do that without being really an expert in pruning or quantization. So, OK, great. So now we have a model that's optimized and converted. So now we want to deploy it, right? So the OpenVINO Runtime API is really the tool or the method for you to integrate this model into your application. Our API, we have an API for Python as well as C++, and in the latest version of OpenVINO, we've aligned those two language APIs so that they all talk about the same concepts, they all have the same class names, the same method names. So it's pretty easy to go back and forth if you don't need to learn two entirely different APIs if you want to implement in different languages. In a very simple example where we're going to do just a classification, you can tell from this example I'm going to run through here that it's really easy to use. So first we import the library, we load our input data, we load the runtime, we read the model from disk, so that the XML file here is the intermediate representation. Out comes the model, then we compile the model, and compiling the model is really where you do that last step where you say, now I'm going to run this model on a specific device. Here in this example, we're using the CPU. Then we're taking the output layer out of that compiled model so that we can run the input data through the compiled model and then grab the result out of the output layer. And so in only 7 layers of code, we go from an image to an output result for classification. So let's look at that compile model line here. This is really where the second stage of optimizations happen. So we already talked about model optimizer, where there's offline optimizations. Those optimizations were not specific to a specific device. This is where the second level of optimization happens for a specific device. And that device can be anything. It could be a CPU, like our cores or Xeons or Atoms. It could be a GPU, like our integrated GPUs or our upcoming discrete GPUs. It could be even like a USB stick where we have an accelerator. And all you need to do is really change that string in the end, and your model will run on that device. What if you want to do something else? What if you want to get higher throughput? What if you have certain operations in your model that run faster on the CPU and other operations in the model that run faster on a GPU? Well, what you can do is use this magical hetero device plugin that will automatically basically partition your model and then run certain operations that run faster on the CPU and other operations on the GPU. So that's one way to get higher throughput. We have another magical device plugin. It's called the multi-device plugin, and that's going to give you better throughput, but in a different way. It's going to take your model and it's going to copy that across the entire model on each device, and then run your inference simultaneously in both devices. So maybe you have 1,000 inference requests. It's going to maybe put 700 on one device and 300 on the other device. So that's another way. And then finally, we have, in our latest version, the auto device plugin, which is the last one of our magical plugin devices, that basically is convenient for an application that can be deployed on any platform, and where the application doesn't even know what kind of devices are available on the platform. Here, you're basically telling the runtime, hey, please take my hint, say, optimize for throughput, and automatically select the best device that works for throughput. Set the most optimal configuration for that device, and then run it on that device, and take care of all the scheduling for me, and so on. So here's how this actually could work. What if you have a model that runs faster on the GPU, but is really slow to load on the GPU, so load and compile? So what this plugin is going to do is going to first compile that network very quickly for the CPU, start inference on the CPU, and then meanwhile, while inference is running, it's going to compile and load that network on the GPU. Once that's done, it's going to switch inference from CPU to GPU so that it actually can run faster, because remember, it's running it can run faster on the GPU. Release the resources on the CPU, and that way you can actually get the overall faster performance, but not incur the delay of loading that network on the GPU. So how about another way of optimizing? And another way of optimizing is optimizing when you have variable input shapes. This is very common for NLPs, where you have variable length input sentences, but also for vision, where you have, for example, with OCR, where you have different shape input patches. And one way you could one thing you could do here is actually reshape the input patches to a fixed size, but that really doesn't work well with OCR, because the text recognition model would just not have very high accuracy. So other ways to work around this is to take a fixed big input buffer, and then every time an inference request comes in, you basically pad out your input buffer with zeros where it's unused. Another way to work around this is have multiple versions of your model, one that handles each input shape. But then, any of these workarounds are usually pretty inefficient and hard to use. So instead, in the latest version of OpenVINO, we've introduced the dynamic shapes feature, where the model automatically reshapes some of its operations as it sees inference requests and input shapes coming in. So you don't have the overhead of reshaping and recompiling the entire model. Finally, in the latest version of OpenVINO, and you might see a pattern here, we're trying to really, in our APIs, to minimize the effort that the developer needs to put in to really get the best configuration for a particular device. And at the most basic level, it really means telling the API, hey, I want to optimize for latency, or I want to optimize for throughput. And from there, the runtime is basically going to set the right configuration, or the most optimal configuration for you. And in most cases, we've seen that results in a near optimal configuration for your device. And that also lets you do that for when you don't know what the device is, right? So this all even works for auto, where the runtime will pick the best configuration for whichever device it picks on the platform. And then lastly, how do you optimize with batching? So for those who are not familiar with batching is where you take multiple inputs and kind of concatenate those into one big input buffer. But typically, the challenge here is to pick the right batch size. How many inputs am I going to collect to get good throughput? Because it really can improve throughput. For example, if you have a discrete GPU, or if you have a very light model, and batching really can improve the utilization of your devices. So today, in OpenVINO, we have a mode that we call automatic batching. And this is really useful and really easy for us, because now we don't need to do the batching anymore. We don't even need to batch up requests. The runtime will do that for you. And to make use of this new feature is really easy. You use the throughput int that we just talked about, and the inference runtime will basically take care of the batching for you. If somehow that automatic batching doesn't work for you, you can obviously turn it off, and that's what I show here on the bottom of the slide. Meanwhile, you can still take advantage of all the optimizations that are being done under the hood for the throughput mode. So with that, I hope that kind of give you a good insight into some of the batteries included optimization tricks that OpenVINO provides to you. And maybe I can hand it over to Ryan to kind of show you how to get started with all of this.
Yeah, and just since we're running out of time, so we have an open model zoo, a lot of pre-trained models that you can download. These are some of our developer evangelists who are, and Paula, who's sitting in the back there, this is her, showing how to use some of the models. So if you want to go to Open Model Zoo, you can go to our GitHub organization. You'll find all of these models and sample code in Python and C++. We also have Jupyter notebooks that you can find, OpenVINO notebooks. You scan this QR code and see how you can use some of these models and try them out. And then I will end with, Jupyter notebooks. There's also a session where you can do work hands-on. We have an Edge AI certification program, so if you're interested in getting certified by Intel, scan this QR code. We also have more information about everything we shared today if you go to openvino.ai. And this is the deep dive session. So on Thursday, you can join Paulo Ramos and Raymond Lowe. They're going to be doing a hands-on session where you can learn how to use auto-batching, auto plugin, using the integrated GPU on your laptop, having a webcam, doing the live OCR or object detection just with the webcam on your laptop, and learn how to use OpenVINO. So that's going to be on Thursday in room 209, 210. And that's it.
Thank you very much, Ryan and Nico. I love magical. That is a great thing, and that's not. I mean, when I first sort of saw neural networks in 2012, I'm like, they're magical, but programming and implementing them is impossible. And now the programming and implementing is starting to be kind of magical, right? It's much easier. Yeah. So a question for you that I have, which is, if you start out with, okay, I've got a TensorFlow or a PyTorch network, right? How much effort is required to then take that and go from that to an optimized implementation? Like, you showed us some of the sequence, but can you give us maybe in some more concrete terms what's involved?
Yeah, I mean, typically, obviously, if you've never used the tool, there's always that learning curve. But once, I would say that within half a day, you can get familiar with the tools. And once you're familiar with the tools, taking a model that's typically a common model that, especially for vision, because vision is kind of such a mature use case, it basically running the tool takes a minute, So you run the tools. You might run it through the benchmark app to see if it's fast enough. Then you might want to do the quantization. You do a level of quantization, and you can do within a half an hour. You have a good feel of what your model can do on a certain device.
And there's a lot of examples. If you go to docs.openvino.ai, and if you check out the Jupyter notebooks, the demos that we have in the Open Model Zoo, you can get started pretty easily and see how to convert a model and load it into OpenVINO.
That's fantastic. Thank you. Other questions for Ryan or Nico? Let's see, several. All right, we'll start here.
Thanks for the presentation. So one question I have is the compiled model. Can you also store it? So if it's fully optimized and compiled, just store it and load it again then?
Yes, we do support that. And in fact, so you can do that explicitly. And then you can ship it and deploy it if you wish. We also have an automatic caching. So if you load a model for the first time on a system, it will cache that to disk, and the next time you load it, it's going to grab it from the cache if it's available.
Which is really useful for a GPU, especially because of the time to compile.
Hi. I'm sorry, that's loud. Could a third-party provider integrate their hardware inference accelerator device to OpenVINO?
I didn't catch it.
Could you say it again?
Yeah, sorry. Could a third-party person enable themselves, their hardware inside OpenVINO?
The short answer is yes, they can. And if you look on GitHub and look in OpenVINO contrib, so we have a contrib repo inside OpenVINO Toolkit, you'll see that there's some third-party hardware plugins. And so yeah, it is possible to write your own plugin for third-party hardware and use it with OpenVINO.
We even have aside from the examples that you can find there, we also have a template plugin that you can basically use as a starting point.
Are there other questions? Yes.
So first, thanks for the talk. It was amazing. My question is, when you say that OpenVINO optimizes for GPU, you actually mean Intel-based GPUs or any NVIDIA GPUs or other types of devices?
Yeah, so we optimize for Intel integrated GPUs, discrete GPUs, as we're coming out with Intel discrete GPUs. And then we also have some support for other GPUs, right?
Yeah, there's an open source plugin in the contrib repo that I mentioned that if someone wanted to use NVIDIA hardware, they could build a custom.
I'm going to make
plugin.
probably an uncomfortable question. So if you had to speak on how does this compare with DeepStream, for example, NVIDIA's DeepStream, in case you're familiar with that.
Yeah, so there's another tool offered by Intel called DL Streamer, Deep Learning Streamer, and it's also based on GStreamer, just like DeepStream. And so, Nico, you're pretty familiar with it, but
yeah, I mean the feature set are very, very familiar. I mean it's hard to compare because we're not comparing apples to apples, right? So it has the same feature set. If you run, it depends on the device you're going to be running it on, but the same types of optimizations are being done for our hardware.
Okay, so I think we are out of time for questions. Intel is booth 305, I believe, and people can stop by and maybe find you or your colleagues there. Is that right?
yeah, there's a few of them in the back here. Wait.
All right, great. Well, thank you very much, Ryan and Nico.
Thanks, Rusty.